Okay, so I hope I am audible. So, um, uh, let's start this tutorial 7, today's tutorial. So, as like to the previous tutorial, in this tutorial also I'll try to discuss some problem which may help you to solve the assignments. And in between, if you have any doubts regarding the course content or anything regarding assignments or any problem, you can ask me, and I'll try to discuss those problems. I'll try to solve those problems. So let's start with some problems. So this is tutorial 7. And today is 7th March. So, and also during the I will not discuss any specific theorems unless it is required. So according to the demands of the problems, I will discuss some problems, theories. Otherwise, I will not discuss any specific theory unless if you are demanding or anything you are not understanding clearly. Those things I'll try to discuss. So, this is the one of the problems. So what this problem says, let E be the projection operator which projects R2 onto the subspace spanned by um, 2, 3 along the subspace spanned by 1, minus 1. Then what is EXY? That is what I have to find. So this some options are given, but obviously here only one option will be correct. So this is a specific type of problem. So we have to solve this type of problem. So let's generally try to do this, and then I'll try to come back to the exact specific problem. So what is mean by first? There is some new terminologies like projections, first terms, and this is the terminology that projections onto the subspace spanned by 2, 3 along the subspace spanned by 1, 3. So these are the terminology which we need to understand first, and then I will try to come back to the problem. So, what is mean by projection? Let V be a finite dimensional vector space. V be a finite dimensional vector space. Then a linear operator E from V to V is said to be projection if E square is equals to E. What is I mean by E square? E square means that is a composition E with composition of E with basically composition of E with E itself. Okay, so this is what it is mean by projections. Okay, so now whenever E is a projection operator, so that is an operator from the vector space V to V, then E must have range. So let R be equals to range of E, and N equals to null space of E. So whenever E is a projection operator and R and N are the null space of E, so then in that case, then in this case, vector space V, in this case R and N, in this case R intersection N must be 0 space, and V is equals to R plus N. So that's why it was, so whenever two subspace W1 and W2 of a vector space V has the property that whenever if W1 and W2 are two subspace of a vector space V with the property that W1 intersection W2 actually zero space, and V is equals to W1 plus W2. Then this sum is called direct sum. Then V is actually this is called direct sum. So first of all, I want to know if R. Note that this is not for any operator. We can't choose an operator and for which range is R and N is a null space. For that operator, this does not hold. That V is equals to V is actually the direct sum of range and null space. That does not hold. This holds for projection operator. Okay, and if we have a projection, if we have a direct sum decomposition like this way, that means you have a two subspace R and N of the vector space V with the property that R intersection N equals to zero space, and V is actually R plus N. In that case, V is actually direct sum of R plus N, and in that case, one can get a projection operator E. One can get an operator E, which will be called the projection, which will satisfy the condition that E square is equals to E. So this holds only for projection operator. And why this holds, you can easily look at that um, if alpha is an element in vector space V, that implies E alpha is in range of E, and that is equals to R, and alpha minus E alpha, this is in the null space of E, which is equals to N. Why this happens? Because E of alpha minus E alpha, that will be E alpha minus E square alpha. Okay, so now E square alpha, E is the projection operator, so that's why E square equals to E. So that's why I will use this fact that E alpha, that is equals to 0. Okay, because as E square is equals to E, because E is the projection operator. So this is the reason that so if for any alpha belongs to V, one can get that E alpha in the range of E, and alpha minus E alpha is in the null space of V. So therefore, any element alpha can be written as E alpha plus alpha minus E alpha. So that means this is in R and this is in N. So that means first property satisfies that V is equals to R plus N. And another thing is that another property is that R intersection N is 0. So why R intersection N will be 0? So why R intersection N will be, that you can easily look at. Suppose if some element beta is in R intersection N, so where R is the range of the space operator E and N is the null space of the operator null space of the operator E, and E is the projection. That means E square equals to E. So if beta is in there, then as beta is in range, then beta must be equals to something E alpha for some alpha belongs to the vector space V, and as beta is in null space, so E beta will be 0, right? But note that E beta is equals to E of E alpha, which is equals to E square alpha, which is itself E alpha, right? But E alpha is equals to beta, but E beta is equals to 0. That implies beta is equals to 0. So that if an element is in an intersection, that implies that R intersection N is equals to 0. So that means whenever you have a projection operator, that is the operator E on a finite dimensional vector space. Here finite dimensional is not a factor because we are not using anything for the finite dimensional, but we will not do anything for infinite dimensional, but that's why I'm assuming finite dimensional. Whenever you have a vector space V and an operator E which satisfies the property that E square equals to E, then that is called the projection operator. But what happens whenever you have a projection operator? Whenever you have a projection operator, as an outcome, you will get, if R is the range and N is the null space, then you will get that V is equals to R direct sum N, and you will get that for every. So then this is called, and conversely, if you have two subspace R and N, any subspace of a vector space V with the property that V is actually direct sum of R and N, that is R intersection N is 0 and V is equals to R plus N, then you will be able to find an operator E, such projection operator E whose range is R and null space is N. So that means then E is called projection onto R along the subspace N, along the subspace N. Conversely, if W1 and W2 are two subspace of a vector space V such that W1 intersection W2 is equals to 0 and V is equals to W1 sum W2. That is, in combinedly one can say that V is actually the direct sum of W1 direction W2, and this fact has a generalization for the k number of cases, but if that is required then I will discuss. Then there exists a projection operator that is an operator E from V to V such that projection means only the fact is that E square is equals to E, which projects onto W along the subspace W2. Okay, so that means that is W1 is equals to range of the operator E and W2 is equals to the null space of the operator E. This is what it is, I mean. So now let's come back to the problem once again. So now this is a type of problem which I will solve now. So what is this problem says? Let E be a projection operator which projects R2 onto the subspace spanned by 2, 3 along the subspace spanned by 1, minus 1. That means R2 is a two-dimensional subspace. Okay. So here you have a one vector 2, 3 and here you have another vector 1, minus 1. It is very much clear that these two vectors are linearly independent. That means one vector cannot be written as a linear combination of other. That means sometimes some scalar times other. You can't write 1, 2, 3 as some scalar multiple of 1, minus 1. Okay. So that's why these two vectors are linearly independent. So clearly these two vectors will form a basis for the space R2. Now if I consider W1 is equals to span of the vector 2, 3 and W2 is equals to span the vector 1, minus 1. So what we have asked to find an projection operator E on R2 such that the range of the operator E should be 2, 3 and the null space of the operator E should be 1, minus 1. Clearly, as I have said, clearly 2, 3, 1, minus 1 is a basis for R2. Okay. Now for any vector x comma y which is in the vector space R2, that can be written as a of 2, 3 plus b of 1, minus 1. So that means one can write it as 2a plus b comma 3a minus b. I hope I've written correctly. 2a plus b, 3a minus b. So now, so what we have to solve a and b for in terms of x, and the 3a minus b is equals to y. So you can add and you get 5a is equals to x plus y. That gives 5x plus y. That gives a is equals to x plus y by 5, and then b can be obtained. B is equals to x minus 2a. That is equals to x minus 2 times x plus y by 5, that is equals to 5x minus 2x minus 2y by 5. That will give me 3x minus 2y by 5. So this is what it is, x and a and b. So that implies xy can be written in terms of x plus y by 5, 2, 3. I think 2, 3 it was, 2, 3 plus 3x minus 2y by 5, 1, minus 1. So we want an operator E from R2 to R2 such that range of E will be span of 2, 3 and null space of E will be span of 1, minus 1. So clearly you can look at carefully that means it will map any arbitrary element xy. You have for every arbitrary element xy it has two parts. One is x plus y by 5 times 2, 3. One is 3x minus 2y by 5 times 1, minus 1. Clearly it will send 1, minus 1 to 0 and E has to be linear operator. So that says that ex comma y should be mapping to this element only, because it will map the other element to 0. That means 2x plus 2y by 5 comma 3x plus 3y by 5. So I hope one of the option of this problem is this 2x plus y. Yeah, this is the final option is the. So automatically all other options will be incorrect. Okay. Okay. So is it clear to everyone, or should I discuss, or is there any issue with some of the problem? If you have any anything you have not understood or not clear, you can ask me now or later or anytime. I'll try to explain once more. So yeah, thank you. So I'm going to the another problem. So what this problem says, let t from R3 to R3 be a linear transformation defined by t xyz equals to x plus y comma z. So that means it is only changing in the first place, other two places are as it is. Okay. So and if s1 is the subspace that is consisting first two entry x comma y and third entry is 0, and s2 is the first x comma 0 comma z and s3 is x y x. So this is something very different. Okay, our subspace of R3, determine which of the following statement is correct. So here it will be only one option. So but still I can try to do in general. So the question was is that which of the this so here it is asked for the invariant subspace. Here it is given that S1 S3 are invariant, S2 S3 are invariant under T, S1 S2 S3 are invariant under T, S1 intersection S2 are is invariant under T. So clearly if S1 and S2 are invariant, then the S1 intersection S2 will be invariant. There is no doubt about this. So let's check one by one whether S1 is invariant under T or not. So for any element in S1 must be look like this way, belongs to S1. So where it will, uh, so recall that I must recall what is mean by invariant subspace. I have already discussed in the previous subspace, but still recall once. Recall that a subspace W of V is said to be invariant if TW is subset of W. That is, if W is in capital W, then TW should be in capital W. That means it will map every element in W to again to an element in W. This is what it is mean by invariant subspace. So as it is giving the arbitrary element in S1 look like this way, so I have to check whether T x comma y comma 0 is also should look like this way or not. This is clearly will look like this way because the action of t is actually t should send xyz to x plus y comma z. So this is clear. So this is again in S1. So that means S1 is invariant. So one element will be in S1 if the third entry is 0. This is what it is by mean, right? It does not saying that the first and second entry of the entry in S1 will be different. That is not saying they can be same. There is no problem. Okay. Now the S2. So what is the element in S2? That x comma 0 comma z, that is in S2. This is the general element. And T x comma 0 comma z, what it is look like? This will be like x plus 0, that is again 0, comma y, that is 0 comma z, because this is what it is T, because T should map x y z to x plus y comma z. So this is again S2. So that implies S2 is invariant under T. Now the third one. Third one says the entry in third S3 is actually x comma y comma x. X comma y comma x is in S3. Then T of x comma y comma x, that is equals to will be x plus y comma x. But now question is whether these entries, this x plus y comma x, this is whether this is in S3 or not, The question is this: if this is there, then S3 will again be invariant. But recall that what are the elements in S3 look like? The element in S3 look like that first and third entry should be equal. This is what it is, the element in S3. At least this is one of the criteria, and this is the criteria. There is no other criteria. The first and third entry has to be equal. But here it is not necessarily. But because if you take y is non-zero, for example, you can take 1, 2, 1. This is in S3, but its image under so basically its image under t 1, 2, 1 is equals to 3, 2, 1, and this is not in S3, right? So that means S3 is not an invariant subspace under T. So that means what we got: S1, S2 are invariant subspace, and S3 is not an invariant subspace. Okay, so one fact I have said little differently, that S1 intersection S2 is invariant if S1 and S2 invariant. That's not always true. I'll check once. So basically S3 is not invariant. So that's why this option is incorrect. That is because here it is first option is says that S1 and S3 are invariant. This is not necessarily true, right? So this is not necessarily true because S1 is invariant, but S3 is not necessarily invariant. But it is asked that S1, S3 are invariant. So that's why it is not true. Similarly, S2 and S3 are not invariant because S2 is invariant, but S3 is not invariant. And clearly S3 is not invariant. So that's why S1, S2, S3 are not invariant. So that's why third option is also incorrect. So automatically the first option will be correct. But I have to check. I'll check that S1 intersection S2 is invariant. So recall that what is the S1? S1 is equals to x comma y comma 0. I think this is what it is, S1. Yeah, such that x comma y is in real, and S2 is equals to middle term is 0. So x comma 0 comma y such that x and y is in R. Okay, this is what it is, S1 and S2. So now S1 intersection S2. So S1 saying that the last entry will be 0 and first and third entry are arbitrary. S2 says the middle entry has to be 0, first and third entries are arbitrary. Okay, so that means S1 S2 intersection S2, that should be like x comma 0 comma 0 such that x is in real. This is what it is, S1 intersection S2. So but now check if an element x comma y comma 0 is in S1 intersection S2, then T x comma y comma 0 where it is mapping. It should be mapping by the formula that x plus 0, x plus y, that's 0, and the y comma 0. So this is what it is as it is. T actually becomes the identity operator on S1 intersection S2. So that's why it belongs to clearly S1 intersection S2. So that says that S1 intersection S2 is invariant. And that is also one can do without, yeah, that is also one can do without doing all this. Just only knowing that. Also, this can be looking, also, this can be done by the fact that S1 and S2 are invariant. Why? Because suppose you have a vector alpha which is in S1 intersection S2, right? So now that means alpha is in S1 and alpha is in S2. So if S1 intersection S2 is invariant, we need to show that T alpha is in S1 intersection S2. This is what I need to show. But as alpha is in S1 and alpha is in S2, then T alpha is in S1 because alpha, S1 is invariant, okay, under T, and T alpha is in S2 because S2 is invariant. So that implies that T alpha is S1 inside S1 intersection S2. So this we don't need to check also. We can say it from these two facts that S1 intersection S2, if S1 and S2 are invariant, then their intersection is again invariant. Okay, this is true. If so, one fact from here one can say is that if S1 and S2 to subspace is invariant under a linear operator T, then their intersection is again an invariant subspace. So that's why the last option is correct. So is it clear or have any problem? So if you are not able to clear, you can ask me later also. Okay. So I'm going to the next problem. So next problem says let V be a finite dimensional vector space over the field F and V is equal to W1 direction W2 some WK. So we have seen one fact that whenever you have two subspace W1 W2, then what is I mean by W1 intersection W1 direction W2. But here it is what is mean by W1 intersection W1 direction W2 direction some k number of. I have said once that there is a generalization of this fact to the k number of subspace, but if it is required then I will discuss. But here it seems to me that it is required. I will discuss. Now so what is the question says that V be a finite dimensional vector space over the field F and V is equal to W1 direction W2 direction WK. If there exist k linear operators E1, E2, Ek on V, then which of the following statement is if there exists k linear operator E1, E2, Ak on V, then which of the following statement is incorrect? Yeah, this is the incorrect option, but it seems to me that question is little incomplete. Question is little incomplete, so let me write correctly. So clearly one can say that either here is the two option you can look at carefully that I equals to E1, E2, Ek and E1 plus E2 plus Ek and another is E1 plus E2 plus Ek equals to 0. So that one of them must be 0. One of them must be incorrect. That's clear. So first two options are not clear. But still the question, I think question is a little incomplete. So let me give some extra condition. If there exist k linear operators E1, E2, in Ek on V such that range of ei is equals to wi for all I equals to 1 to k. This is what it is belongs to the question. Then what is the correct option? Then okay, then obviously this is the incorrect option. So let me this is itself a theorem, but let me write what is I mean by this direction. Okay, so so let V be a vector space. Let V be a vector space, finite dimensional V be a finite dimensional vector space. W1 all the way WK are subspace of V. Then W1, then W1 all the way WK are said to be independent, are said to be independent if for any vector alpha is equals to alpha 1 plus alpha 2 plus all the way alpha k, which belongs to W1 plus W2 plus all the way WK, if alpha with alpha is equals to 0, then we must have each alpha is equals to 0 for all I equals to 1 to k. That means suppose you have k subspace W1, W2, WK and you are considering their addition like W1 plus W2 plus WK, and you are taking a vector alpha is in that space like that the summation some space that W1 plus W2 plus WK. Now if alpha is equals to alpha 1 plus alpha 2 plus alpha k, where alpha is in Wi, if alpha is equals to 0 implies that each of alpha has to be 0, then we say W1 WK and W1 W2 WK are independent. So if you carefully look at carefully, if k is equals to 2, so then we have two space W1 plus W2, and in that case if alpha is equals to alpha 1 plus alpha 2 is equals to 0, then one alpha 1 equals to 0 and alpha 2 is equals to 0. This is what it is I want to mean, and this fact itself means that W1 intersection W2 is equals to 0, because if W1 intersection W2 is not equals to 0, that means there exists some non-zero vector beta, then one that means beta is in both W1 and beta is in both W2. then alpha, if I write beta minus beta, which equals to 0, this is alpha 1 and this is alpha 2. That means alpha 1 and alpha 2, each of them individually not being 0, their summation is 0. So that means this will violate the fact that alpha 1 plus alpha 2 equals to 0 implies that alpha 1 equals to 0, alpha 2 equals to 0. This if W1 intersection W2 is non-zero, if W1 intersection W2 is a non-zero subspace, then this should violate the fact that alpha 1 plus alpha 2 equals to 0 should imply that W alpha 1 equals to 0, alpha 2 equals to 0. I hope this is clear. So that means what I just want to say is that this linearly independent fact is actually we have already discussed with this, that W1 intersection W2 equals to 0. If W1 and W2 are two subspace, then their intersection is 0. This is the what it is mean by linearly independent in whenever k is equals to 2. But here, whenever k is arbitrary, in that case, it will automatically say that Wi intersection Wj equals to 0. Okay, for all I not equals to j. But that is not all. We can say little more. So, and this fact is equivalent. This fact is equivalent to this, that Wi intersection W1 plus all the way plus Wi minus 1 plus Wi plus 1 all the way plus Wk. This is equals to 0 space for all I equals to 1 to k. So this automatically gives, this statement automatically gives that Wi intersection Wj equals to G. This automatically gives this in particular provides that Wi intersection Wj is equals to 0 for all I not equals to j. Okay, but this fact that if Wi and Wj are mutually disjoint, that does not imply, this is called mutually disjoint. If Wi and Wj are mutually disjoint, that does not imply that Wi intersection W1 plus W2 plus Wi minus 1 plus Wi plus 1 plus Wk till Wk, that is has to be 0. That intersection has to be 0. So this is not what it is. I mean, this fact will give this one, but this fact will not give this one. Okay, that not necessarily, unless it is r equals to 2. I mean k equals to 2. Whenever it is k equals to 2 situation, whatever it is. So my point is that this is linearly independent means this one. Okay, or in another word, there is another word that if W and W2 Wk are subspace and equivalent to that, this is equivalent to that if beta I are basis of Wi, then beta 1, beta 2, all the way beta k. This if I replace one by one of the basis and next another basis, next another basis, this way, this is linearly independent. So any of the cases, this is any of the cases one can write that W1 direct sum, W2 direct sum all the way Wk. Okay. Now the fact is that, so if I have so here you can consider, suppose let V is equals to, let V is equals to W1 direct sum W2 plus all the way direct sum Wk. So what it is says, for without loss of generality, if I take W1, then this subspace, this direct sum this, so that means we will have a projection E1. E1 is the projection, onto W1 along the subspace W2 plus Wk. So similarly, for each I, Ei will be projection on Wi along the subspace, this subspace, that W1 plus W2 plus Wi minus 1 plus Wi plus 1 plus Wk. This is this way. So what my point here it is that these are the suppose Ei. That what it is, because in the first questions I have tried to say that whenever you have a direct sum, you can have a, whenever you have two subspace W and W2, their intersection is 0 in that way, so you will get an projection operator. So you get projection operator E1, E2, Ek, and each of the cases Ei are, so for range of Ei is actually Wi, and null space of Ei, that is equals to W1 plus direct. This is just, you can write in sum also, wi minus 1. Here it is still, it will be direction, there is no problem, but direction is not needed, plus 1. So if not needed, then I will not write, then that's not necessarily. Okay, let me just a minute. Yeah. So W1 plus Wi plus 1 plus all the way plus Wk. So this is what it is, you can write. So this is what it is. So now these are the operator, because Ei are the projection. Okay. So now I think I have written that range of Ei is equals to Wi. Then what are the property it will satisfy? Then clearly Ei are the projection, so that's why Ei square is equals to, clearly Ei square is equals to Ei. Okay, but whether what is Ei Ej if I equals to not equals to j. So if I not equals to j, then what we can say by Ei Ej. So note that Ei Ej on an element alpha. So alpha should be look like alpha 1 plus alpha 2 plus all the way plus alpha k, where alpha I is in wi. So now look at alpha j will map every element to 0 except alpha j, right? So that means alpha I, ei, this will be like ej into alpha j, right? But alpha j is in wi, so that's why alpha j is in wj, so that's why as ej are the orthogonal position on wj, so it will send alpha j to alpha j, ei alpha j, but I not equals to 0. So ei should map any element in wj to the 0. That is 0. So that means if I not equals to j, so this will be 0. Okay. So whenever you have a projection, it will, suppose you have a projection. Whenever you have projection, there is two things. One is range and one is null space. So that means it will map range element to the itself. Because if it is in range, then it will map to that element, because that is what we have seen. Because if you look at recall previous whatever we have done, if beta is in range of A, then E beta should be beta itself. Why it is? Because if beta is in range of E, then beta must be equals to some E alpha for some alpha is in vector space V. Now what is E beta? E beta is itself E square alpha, that means E alpha, because E is a projection, because E square equals to E, and that is beta. So that means a projection will map every element in the range to the element itself, and every element in the null space to 0. And range and null space direction is the full space. This is a little interesting. So that's why this is a little interesting. So these two options, first two options are incorrect. Clearly, these first option are correct. This is correct. This is correct. Okay, because projection ui square equals to this linear operator on V such that range of equals to this. Now the third option is that projection. Third option is that I equals to E1 plus E2 plus EK. So whether this is true or not. If range of Wi is equals to range of Ei is equals to W, note that range of Ei is equals to Wi. Okay, and also we know that W1 direct sum W2 direct sum Wk, that is equals to V. So now question is, what is E1 plus E2 plus all Ek as operator should be? That will apply on an element alpha. That means E1 plus E2 all the way Ek, that will map alpha 1 plus alpha 2 plus all the way alpha k, right? Where alpha I is in Wi, and alpha is actually this is the sum. Okay. So now each of the operator will, E1 will apply on full this alpha 1 plus alpha 2 plus alpha k, but Ei is an projection. So that's why E1 should be mapping alpha 1 to alpha 1, and all other entry will be 0 under E2 E1. So this will be E2 alpha 2 all the way plus Ek alpha k. Okay. So now note that alpha 1 is in the range of Ei, so that means in Wi. So that means this will be like alpha 1 plus alpha 2 plus all the way alpha k, this is equals to alpha. This implies that E1 plus E2 plus Ek, this is equals to identity. So this is means this option is correct. So this option is the incorrect option. So but here it is asked to incorrect option. So as a option, correct option for these questions is, so this is the correct option for these questions. What is the correct answer to this question? Correct answer to this question is the last one, because e1 plus e2 plus ek is 0. That's not correct. Okay. So this is what it is. Is it clear? Okay. So if you have any doubt, you can ask. Even it is very easy. Even it is very trivial. So let's go to the next problem. So what is the next problem? Says if E is a projection operator on a finite dimensional vector space V, and fx is equals to 2 to the 2x to the power 7 minus x to the power 6, 4x to the power 5, 3x to the power 4 minus 2x cube plus 5x square minus x plus whatever it is, some polynomial is there. Then f of E is equals to ai plus be. Then where AB? So I have to find. So this is very trivial questions. You can easily solve. So fx is given by this. E from vector space V to V is a projection. Then E square is equals to E, right? So now f of E is equals to 2 e to the power 7 minus e to the power 6 plus 4 e to the power 5 plus 3 e to the power 4 minus 2e cube plus 5e2 3e plus 9 identity. Okay, this is what it is. So now e to the power e square equals to e. So basically what you'll get, suppose you have e7. So what you'll get, e5 e square, that is equals to e again. So basically you can break it like e square e square e square e, and then you'll get e square is e, all of them is, then you'll get e, then you'll get again e square and e square, that is equals to e, that is equals to e square is equals to e. And e to the power, suppose 4, I'm just asking for the even powers, for example, then e square, so that means e that is equals to e square, that is equals to e. So what you got, even or odd doesn't matter. Okay, every time it will be e, even or odd doesn't matter, every time it will be e, but except e0. If I have e0, that is identity, that's separate thing. Okay, so basically what I can write here is that, note that I will not write this. This is very much clear, you can just compute. This is not, note that what I can say from here, note that e to the power n is equals to e for all n greater than equals to 1 integer, obviously, for all in positive integer is the for all positive integer. This is clear, right? So for all positive integer, what we'll get, e to the power n is equals to e. Okay, so that means this will be 2 times e minus e plus 4e plus 3e minus 2 times e plus 5e minus 3e plus 9 identity. So this will be like 2 minus 1 plus 4, 2 minus 1, 1 plus 4, 5 plus 3, 8 minus 2, 6 plus 5, 11 minus 3, 8 plus 9, 8e plus 9i. So this gives a is equals to 9 and b is equals to 8. So the third option is the correct option. So this is very trivial. I hope there is no doubt. Even still, if you have doubt, you can ask. So let's go to the next problem. Oh, sorry, this is the. So this is something maybe interesting. So what it is this problem says, let T be a linear operator on a finite dimensional vector space V, and let V is equal to W1 direction, W2 direction, WK, and E1, E2 be the projection of V on W1, W2, WK respectively. Then which of the following statement is or are correct? Okay. So this is also will be very interesting. So but let's see. Let P be a linear operator on a finite vector space V, and V is equals to direction W1, W2, WK, and E are the orthogonal projection, not orthogonal, projection of V on W1, W2, WK. Then what we have seen? We have seen that we have seen that first EI square is equals to EI. This is the first option. Second option, EI EJ is equals to 0 if I not equals to 0. And the third option is that E1 plus E2 plus all the way EK, that is equals to identity, right? We have all these facts. Then which of the following statement is or are correct? This is what it is I have asked. First question is that if TEI is equals to EIT, then WI is invariant under T. Okay, so WI is actually range of EI. So here I will give something. Uh, here I will do. So here is the which of the following statement is or are correct. So clearly the third option is correct. That is what we have already seen, right? In the previous problem, I have seen that I equals to E1 plus E2 plus EK, where I is the identity operator. And the first option. So here for the first option, here it is clear that EI is actually commutes with T. This is what it is mean. Then range of EI is invariant under T. So for this first operator for option A, so I will give some little more general. Let T and U from V to V be linear operator. Okay, and PU is equals to UT. That means commutes. Then then range of U and null space of U is invariant under T. This is what it is. So range and null space of U is invariant under T. So why it is? Suppose alpha is in so beta is in range of beta is in range beta is in range of U. Then beta is equals to U alpha for some alpha, U alpha for some alpha is in the vector space V, right? So then T of beta is equals to T U alpha, right? But U and T are commute, so that means we can write U T alpha, right? So now T alpha is in vector space V, and this is in the range of U. So that means range of U is invariant under range of U is invariant under T. Similarly, if alpha is in the null space of U, then U alpha is equals to 0. Then what I want to show is that T alpha is equals to 0, right? Because sorry, T alpha is in the null space. We want to show T alpha is in the null space of U. That is U of T alpha, that has to be 0, right? So, but that is the, and indeed this is the case. So let me write the correct statement here. Indeed, U of T alpha, this is equals to T U alpha because the U and T commutes, and U alpha is equals to 0. That means T is 0 and T is linear operator, that will be 0. Okay, so that means T alpha is in the null space of U. So that means what I just want to prove that range and if two operator T and U commutes, then range and null space of an operator is invariant with respect to the other operator. So as a linear operator commutes with itself. So that's why for any linear operator T, its range and null space is invariant under that operator. So now, what is the first option? Why I am doing this? Because first option is something can be derived from here. So in particular, if TEI is equals to EIT, that should imply that WI, which is actually the range of EI, is invariant under T. Okay, I hope this is already the first option mean. So first option is correct. Now second option, if TEI is equals to EIT for some I, then Wj, which is for where j is not equals to I, is invariant under T. That's not necessary. Okay, that's not necessary, and that will not hold. In fact, so that's why it is incorrect option. And third option is correct. Now the last option, if each Wi is invariant under T, then T commutes with Ei. That is also true. So let me check this one. I hope that is true. So last option is an interesting option. If each Ei is if each Ei is invariant under T, sorry, each Wi is invariant under T, right? This is what it is. The question is that if each Wi is invariant under T, then T commutes with each Wi. If each Wi is invariant under T, then with each Ei. Okay, this is what it is. I have to prove, right? If each T commutes with sorry, if T commutes with sorry, if Wi is invariant under T for each I, then T commutes with each Ei. Okay, this is what it is. I have to prove, right? So I have to prove that TEI is equals to EIT. This is what it is. So basically, we need to prove this is what it is. I have to prove. So basically, we need to prove EIT. So let me. So for any alpha is in vector space V, alpha is equals to alpha 1 W, and EI alpha is actually the alpha I. Okay. So then T of EI alpha this is where it is, but is in Wi. So this then is in Wi by the assumption that um, Wi is invariant under T. So as the EI alpha, it is in the Wi, and Wi is invariant under T. So T of EI alpha, that has to be element in the that has to be in the Wi. Okay. So now T of alpha, that is equals to T alpha 1 plus T alpha 2 plus all the way plus T alpha. Okay, this is what it is. That's clear. Okay, that's true. I have to prove T of EI is equals to EI of T. Okay. Now Yeah, I have to prove TEI. So basically, let's find what is E of T alpha, right? So I of T alpha is EI of T alpha 1 plus EI of T alpha 2 plus all the way plus EI of T alpha k. But note that T alpha I is in Wi and EI is the orthogonal projection on Wi. So that means EI will map any elements in Wi to the elements itself. Otherwise, it will map to 0, right? So that basically it will map EI to T alpha I, which is actually equals to T alpha I. So that says that T of EI alpha that is equals to EIT alpha. This is what it is, right? This one. So for all alpha in V, so that implies that T of EI is equals to EI of T on V for all K. Okay. So what is I am trying to say here it is that, so basically what I have to say that, note that if you have a linear operator T on a vector space V, which is direct sum of W1, W2, Wk, something like that. So in that case, if E1, E2, Ek are the orthogonal projections on the subspace Wi, so in that case, what I can say is that each Wi, if T intertwines with Ei, then if T intertwines with Ei, that means Ti equals to Eit, then Wi is invariant under T, right? But here, if each Wi is invariant under T, here for each it is required. For each Wi is invariant under T, then T should commute with each Ei. But if suppose you have a some fixed something like W1 is invariant under T, okay, that does not imply that T will be commutes with E1T. That is not does not imply. Okay, this should hold for all the Wi. Okay, this is what it is just under. If this holds for all Wi, that Wi is invariant under T, then we will have that T of Ei is equals to Eit for all alpha. Here it is for all I. This is what it is needed. So how this is proving that this is very easy. So basically I want to say that this is individually is not possible. That if I know that fixed Wi, one fixed Wi, for example W1 is invariant under T, that does not imply that T will intertwine with T1. We have seen that we have seen if T is intertwining with a single EI, that will say that Wi is invariant under T, right? But the converse is not true. This is what I want to say. If Wi, fixed Wi is invariant under T, that does not imply that T will intertwine with Ei. But if this is true for all I, then we will have this for all I. This is what it is I want to say. Okay. So I hope this part is clear. This part is very easy. For any alpha is in alpha 1 to alpha 2 alpha k, as alpha is in range of, then Ei alpha will actually, that alpha is actually Ei alpha. So basically T of Ei alpha will be alpha T of alpha. This is what it is, and T alpha in general look like this way. So Ei T alpha should be like this way, and as T alpha I is in range, because this is what it is in our assumption. That assumption is that T of alpha I is in the Wi, because T maps every Wi to Wi. So that's why here is all the fact is using. Here is the fact all the Wi is mapped under T to the Wi. That fact is using here, and it is saying that it will Ei will map only the T alpha I and all other, and it will map all other entities to 0. So is it clear what I just want to trying to say? So here two-way things is not true, that if T commutes with single Ei, that will imply range of that single Ei is invariant under T. But if specific Wi is invariant under T, that does not imply that T will commute with Ei. So okay, if there is any problem with anyone, so you can let me know. I will try to explain more little. So this is another problem. What it says, let u1 and v1 are two subspaces of a vector space V. Okay, and such that V is equals to u1 sum u2. Here it is not direct. That means their intersection need not be 0. Okay. Then which of the following statement is or are correct? If the u1, v1 and w are subspace of V such that u is equals V is equals to u1 direction w is equals to v1 direction w, then u1 is equals to v1. This is what first option. Second option, okay, let me check the first option. Okay, so whether first option is correct or not. So here it is says that V is equals to, so let me check one by one. So first here it says u1 and v1 to subspace of a vector space V, and V is equals to u1 sum v1. Then which of the following statement is or are correct? So first option is that u1, v1, w are subspace of V. They are subspace of V, and V is actually something like u1 direction w and v1 direction w, something like that, and w is some specific fixed. Then u1 is equals to v1. So note that here this option is incorrect. So why this is incorrect? One can create a counter example. Though it seems to be correct, but this is incorrect. It seems to be that correct, but this is incorrect. Note that they are sum, but they are not direct sum is something very different. They are not just usual sum, okay? Element sum, they are subspace sum. So for example, let's take V option A. Let V is equals to R2, okay? And W is actually span of, for example, 0, 1, right? Yeah, 1, 0, okay? And W and U1 is equals to span of 0, 1, right? And W to V1 is equals to span of 1, comma 1. Okay. So clearly, look at carefully that any clearly W intersection U1 is G0, W intersection U1 is equals to 0 space, because there can't be, you will not be able to find, I'll check once, and V1 intersection W, that is also 0 space. Okay, why? Because if an element X alpha must be some 1 0 and scalar multiple of, if alpha is in W intersection W u1, so that means alpha is equals to something like c1 comma 0, and alpha, and also as an element in W, and as an element in W1, this will be like C2 comma C2, and if these two are equal, that would say C2 equals to 0, right? And once C2 equals to 0, this will be completely 0, and that will force that C1 equals to 0. Because why C2 equals to 0? Because okay, let me clearly mention. I just want to say that W intersection U1 is equals to 0. If alpha is in W intersection U1, then alpha being an element in W, that will be some scalar multiple of 1 comma 0. So alpha is equal to something like C comma 0, right? For some C in real line, and alpha also, alpha being an element in U1, alpha is equal to something like C2 comma C2, because that will be of scalar multiple of 1 comma 1. So now alpha is equals to C comma 0 is equals to C2 comma C2. Now if we compare the second coordinate, we will get C2 equals to 0, and that will force that alpha is equals to C comma 0 is equals to 0 comma 0, and that will force that C is equals to 0. So that basically says that alpha has to be 0. There is no other option. Okay, so this will say that W intersection U1 is equals to 0. And similarly, you can check that, okay, I have checked it with V1, I think. W intersection V1. Okay, this is V1. I have checked with V1. Okay, so this is V1. So clearly, that says that W intersection V1 has to be 0. Okay, there is no, and clearly W intersection u1 will be 0, there is no doubt, because they are completely linearly independent. You can look at carefully. Okay, so that's why. And also they spans, also note that 1011 they spans, also 1001 is a basis of R2, and also 1011 is a basis of R2. So that means W1 direct sum, W direct sum U1 is equals to V, and which is equals to W direct sum V1. But clearly W1 is not equals to V1, because entries in W1 actually scalar multiple of, the entries in U1 actually scalar multiple of 0, 1, and entries in V1 actually scalar multiple of 1, 1. So that's why they are not equal. You can clearly, they are not equal, because scalar multiple, they equal only the 0 element is the equal. There is no other equal element. Okay. So that's why the first option is incorrect. Okay. The second option is that if V is in capital V and V is equals to U1 plus V1, and U2 plus V2, for some U1, U2 is in U, and V1, V2 for some V, then U1 equals to V1 and U2 equals to V2. That is not necessary. Okay, that is also not necessary. U1, U2 is in U, capital U1, and V1, V2 is in capital V1. Then U1 is equals to U2. Then U1 is equals to V1 and U2 equals to V2. This is the second option I have to check. Okay. So in this example it will be, but in general it not. Okay, no. U1 and V1 are specifically fixed. Okay. Okay. U1 minus U2 equals to 0 and V1 minus V2 is equals to 0. So basically, if I get something like that, U1 intersection U2 V1 has some common element, then okay. So for the second option, I hope second option is incorrect. So here it is option B. I'm writing option B, that gives V is equals to U1 plus V1 equals to U2 plus V2, where U1 comma U2 is in, where U1 comma U2 is in capital U1 and V1 comma V2 is in capital V2. Okay, capital V1. This is what it is giving. So now I have to give some counter example here. This is also false. So let's take U1 is equals to anything else given here. V is equals to U1 plus V1, that is also given. So let me write U1 is equals to span of 1 comma 0 comma 0 and 1 comma 1 comma 0, or 0 comma 1 comma 0, 0 comma 1 comma 0. Okay, and V1 is equals to, this is what it is, U1, and V1 is equals to span of 0 comma 1 comma 0 and 0 comma 0 comma 1. This is what it is, V1. So now the question is that so clearly U1 plus V1 is equals to V. V is the vector space. Here it is, I am taking R3. So V is equals to R3. This is the vector space, and I am taking U1 is the space spanned by this, and V1 is the space spanned by this. Clearly U1 plus V1 is equals to the vector space V. Now if an element, I am writing an element U1 element V is in, now the question is that any element V is in U1 plus V1 and U2 plus V2. For some U1 U2 is in there, so that should imply that, okay, that I think not necessary. So let me write this one. So U1 I have to write as a scalar multiple. So let's write this one as 1 0 0 plus 2 times 0 1 comma 0. This is what it is, U1, small u1, and V1 is equals to just 0 1 comma 0 and plus 2 times 0 comma 0 comma 1. Okay, this is v1, and so what I can write as u2 is equals to, yeah, u2 is equals to 1 comma 0 comma 0 plus 3 0 comma 1 comma 0, and v2 is equals to 2 times 0 comma 0 comma 1. So this is what it is I have written. So clearly note that u1 plus v1, which is equals to 1 comma 0 comma 0 plus 3 0 comma 1 comma 0 plus 2 0 comma 0 comma 1, and that is clearly same with the fact that u2 plus v2. Okay, but now u1 is not equals to, question was whether u1, question was what are the options, that u1 equals to v1. So clearly u1 is, sorry, u1 is equals to u2, u1 equals to v1 and u2 equals to, I think this is the incorrect option, u1 equals to u2 and v1 equals to v2. This is the option here it is giving, that's definitely incorrect, there is no doubt. But even the more, this is in fact, this is clearly incorrect, there is no doubt. But I think this is the option maybe a little wrong, that u1 equals to u2, v1 equals to v2. Whether this is option. Okay, so clearly u1 is not equals to u2 and v1 is not equals to v2. So that's why the second option is also incorrect. Okay, now let's go to the third option. Here it is that v is space of all real valued continuous function, and w and w e and wo be the subspace of even and odd functions. So what is even and odd functions? A function is even if f of minus x equals to f of x, and odd if f of minus x equals to minus of fx. I'll mention once. Be the subspace of even and odd functions of v respectively, then v is equals to we union w naught. That is also incorrect, but the second fact is correct, that I will prove. So basically here v is the space of all continuous functions, I think, or let me change, v is the space of all real valued continuous functions, over where v is the space of all real valued continuous functions. Okay, v be the space of, so here it is giving v be the space of all real valued continuous functions. Okay, then v and we is the space of all even functions, so that means all those functions in vector space v such that f of minus x is equals to f of x for all x is in real number. I mean, this is general, there is no, okay, this is what it is. And wo, that is the odd function, space of all odd functions, which is equals to f of f in v such that f of minus x is equals to minus of f of x. Okay, so this is the space of all odd functions. Now first of all, here it is one first third option was giving that v is equals to we union w naught. First of all, this we and wo, that means space of all even function and odd functions, they are disjoint. Okay, let me do this and note that we intersection wo is actually only contains the zero space. That is, if indeed if f is an element in we as well as wo, I think I have said this one once. F of x is equals to f of minus x is equals to f of x as it is in even function. Also, f of minus x is equals to minus of f of x as it is in odd functions. So that will give that f of x is equals to minus of f of x, and that will give that f of x equals to 0. So that means only the zero function is in intersection, otherwise there is nothing. And the two subspace is, here is union, here it is giving union. First of all, union of two subspace of a vector space is again a vector space if either one of them is contained in other, and there is no other options. This is if and only if. We have already proved, and this probably in the first tutorial proved that if W1 and W2 are subspace of a vectors of V, subspace of V, then W1 union W2 is again a subspace of V if and only, this is completely if and only, if W1 is contained in W2 or W2 is contained in W1. But this is not the case in our situation. But this is not the case in our situation. Situation. So why this is not the case? You can clearly, you can clearly note that sine x, I think sine x is odd function. Odd function can't be in even function and even function can't be in odd function because their intersection is zero. If there is something common, that has to be zero, but this is not the case, right? From here you can also say, here it is given that we have proved that WE intersection W naught equals to zero. So if it is, if their union is a subspace, V is a subspace, if their union is a subspace, that is WE is actually contained in WO, that implies that WE intersection WO has to be WE, right? This is what it is because W is contained in WO. So that, but this is equals to zero. That means there is no even function except zero. But that's not true. Cos x is the even function, x square is the even function. In fact, x to the power any even power is the even function. So but that's not true. And similarly, other around is also not true because sin x is the odd function and any odd power of x is an odd function. So that's why it is not true. So here one fact, and but what I just want to prove is that that's why the option C is correct. Third option is incorrect. Now the fourth option. Fourth option is that claim is that V is actually WE direction WO. So clearly, I have in the beginning of this today's tutorial, I have said that if W1 and W2 are subspace of V, then we can write the V W1 direction W2 is equals to V if and only this direction means what I just mean that W1 intersection W2 has to be zero space and W1 sum W2 has to be V. We have already seen that WE intersection W naught is equals to zero. Intersection W naught is equals to zero space. But any function, if I can write that V is actually the sum of two elements, one is coming from W1, another is coming from W2, then we are done. Okay. So for any element, for any f is in V, we can write f is equals to f of x is equals to basically f of x is equals to f of x plus f of minus x by 2 plus f of x minus f of minus x by 2. Note that if I write this is as the gx and this is as the hx, this is gx and this is hx, then clearly g of minus x is equals to f of minus x plus f of x by 2, which is again gx, and h of minus x, which is equals to f of minus x minus f of x by 2, which is equals to minus of f of x minus f of minus x by 2, that is equals to minus hx. So that's why this is even function, this is odd function. So basically what I have able to prove that this is contained in W1 intersection W2. So that means, that says that V is equals to W1 sum W2. So that says that V is actually W1 direction W2. So the third option, fourth option is the correct option. This is the correct options. So what is the important point here is that whenever you are doing in set theory, it sometimes feels that sum is something like equal to union. Okay, but whenever you in the vector space settings, equal is something very negligible things. Okay, sorry, so union is, sometimes it feels that sum is something like union. Okay, sum, suppose to set sum and to set union is something. Suppose you have a two set and their union is something taking all the region, and it seems to me that sum is something that should coincide with the union. But in vector space settings, union is something very negligible fact, because that most of the time uh, does not form a vector space, okay, unless one is containing other. But sum is something very different. Sum can happen, and some, like two subspace can be add, but two subspace can't. I mean, in general, it's not something like you can't take union, because you can take union, but union need not be a subspace. And whenever that is not subspace, that is not of our use. Okay, so that's why sum is, these two facts are very different in vector space setting. These two facts, that union and add, here it is, even if you consider it as a sum, these two facts are very different. Okay, in our settings. So is it clear? Okay. Okay, let me go to the next problem. So you can read the problem. I'll just, okay, so what this problem says, let T be a linear transformation from R4 to R4 such that the matrix representation of T with respect to the standard order basis, that is 1 0 0 0 0 1 0 0 and 0 0 1, some that, then which of the following statement is or are incorrect? Okay, this is what it is asked. So here basically, here it is asked to find the invariant subspace. So invariance means, once again, that if W is in capital W, if W is subspace of V, then TW should be in W again, that is in capital W subset of W. This is what it is. So it can be like something like that. So this is what it is, invariant. So basically, I have to check which one is the invariant under T. This is what it is. You have to find. Okay. So here A is giving like this way. So um, I'll be trying to write very shortly. So in particular, T is the linear operator from R4 to R4, and T maps any vector X in R4. R4 is a column vector to AX. Okay. So which is equals to A is means that 2 0 1 3 0 4 minus 1 2 1 minus 1 3 1 0 2 0 5. So it will map any general element x1, x2, x3, x4 to, where it will map to general element that 2x1 plus x3 plus 3x4, comma, 4x2 minus x3 plus 2x4, or I think xyzw. If I write it is something like different, xyzw, that would be better, I think. xyzw, x, y, z, w. So this will be like 2x plus z plus 3w, comma, 4y minus z plus 2w, comma, x minus y plus 3z plus w, comma, 2y plus 5w. This is what it is. Okay, ax looks like this way, 2x plus z plus 3w and 4y minus z plus 2w, x minus y plus 3z plus w, 2y plus 5w. Okay, this is what it is. Now, so so we have this one. So let me check. S is the set, that is the first middle two entries has to be 0, and first entry and second entry look like this way. So what will be T of, for any element, uh, element any element alpha is equals to minus x comma 0 comma 0 comma x is in S1. I'm writing this one as S1 and S2, S3, S4. So, so what it will be like T of alpha? T of alpha will be like 2x minus 2x plus z, z is x again, and w is 0. No, sorry, this is where is the mistake I made. W is 3x, right? This is what it is. Okay, I think I'm making unnecessarily tough this one. So let me check one by one. So this is the what it is. So if I multiply x, we have the matrix this one 2 0 1 3 0 4 minus 1 2 1 minus 1 3 1 0 2 0 5, and I have to multiply it is minus x 0 0 x. This is what it is. So what it will be? It will be like minus 2x plus 3x and just 2x, and next one is the minus x plus x, and next one is the 5x, right? So this will be like x 2x 0 5x. So this is clearly not in S1, because any element in S1 should be look like this way, but the final element, what is the final result coming here, this one is not in that form. So that says S1 is not invariant. So as a option, this is invariant, not invariant. As a option, this is correct option, because here it is asked to find the incorrect options only. Okay, this is the problem number 7. Yeah, so S was not invariant. So okay, I think there's all the options is correct, I think. Okay, so next one is that x minus x. So I'm just doing like here directly x minus, next option is 0x minus x. Okay, 0x minus x 0. I think this is the 0x minus x 0. So what it will be? It will be equals to just it will be like minus x first term, and uh, minus x first term. Okay, yeah, minus x first term. Second term will be like 4x minus x, that is 3x, and so it is already not equal. But still, let me complete this one. Minus x plus x 0, and the first, which one? Oh, sorry. Yeah, thank you. I'm just doing the above one. Okay, sorry, that's the problem. Okay, sorry. So this will be first one will be minus x 0 1 minus x. That's true. Second one will be 4x minus x 5x. That's true. 5x. And third one will be minus x plus minus 3x minus 4x. And fourth one is just 2x. So again, this is S2 is not invariant. So as a option, second option is also correct. Third option is 0 0 x minus x. 0 0 x minus x. So what it will be? It will be like x minus 3x. That will be like minus 2x, and next one is x minus x minus 2x minus 3x, and 3x minus x, that is 2x, and last one is minus 5x. I hope I am correct. So that is again imply that S3 is not invariant. So that's why as option this is correct. Yes, third option is also correct. X minus x is the first one. So let me write once again the matrix, because this is becoming very long. So 2 0 1 3 0 4 minus 1 2 1 minus 1 3 1 0 2 0 5. This was the, and the x minus x 0. X minus x 0 0. So please check what I am calculation doing, whether that is making a very easy mistake or not. This is like x minus x 2x. This is like minus 2x. So again, S4 is not an invariant subspace. case 4 is not invariant under T. So that's why all the options are correct here, but none of the subspace are actually invariant. This is what it is. Sorry, as an option they are correct, but they are not invariant. None of them are invariant basically. Okay, this invariance is not happening here. So is it clear? This is very simple, but still if you have any doubt or anything, uh, okay, I will take 2 minutes. Please wait.
Yeah. Sorry for the inconvenience. So let me go to the next problem. So this problem I have
Sir,
clear.
can you write one matrix 4 by 4?
One second, one second.
Sir,
Yeah.
can you write one example? Just I have not understand.
Okay, okay, just one
Can
minute.
you write 4 by 4?
One second, one second, one second. I'm like having some problem with.
Can you write 1010 row wise?
One second. I don't know why I'm echoing myself.
Huh, 02 01, right?
01
Huh?
0010 1002.
Huh.
And
So what?
inside column vector will be x y 0 minus x.
This one, right?
Can I say it is invariant?
Acha, this space is invariant or not. Elements looks like this or this is. So you can check like x first entry will be like x,
2y
and
minus
second
x
entry will be 2y minus x, third entry
0
is 0, and fourth
minus
entry
x.
is minus x, right? Yeah,
Mhm.
minus x.
Can I say
So yeah, indeed this is invariant subspace, because
why
why this is invariant subspace. So here space is actually the elements looks like this way, such that x and y are real. This is what it is. So two independent variables. So elements in the here it will be look like elements here are
but
look like actually
but
that
there were x and y are individual
still
independent.
okay. That doesn't matter. Yeah, individual.
But
Here
here 2y minus x is
that's
dependent
not a
on
problem.
x.
Elements in S are what is the elements in S? That first entry and the fourth entry is related by this fact that first what if first entry is A, the fourth entry will be minus A. And third entry has
Hmm.
to be 0, and fourth entry
Hmm.
is independent of x. That can be depends, I mean, that can be something that doesn't matter. So any element which will look like this way, that is in the S. Now if we take an alpha in alpha is equals to something like that x comma y comma 0 comma minus x, so then
Hmm.
what we got here actually a alpha, that element is also satisfying this property. Okay, it
Okay.
is not saying that if I can write this one as a new element y dash, right? Is that getting
Yes.
bothering to you? I
Yes.
mean,
Yes.
something like that. You can say here is the s, and here is the s again. So
Hmm.
same s. So t is actually mapping a is actually mapping s to something inside, not full.
Hmm.
2y minus x is an element. That's all.
Not
But
same, but
not
look like similar.
no no no. I'm saying that as a subspace, S and S is a subspace. Okay, S is a subspace on the vector space
Hmm.
of a vector space V. You have S and you have here S, and you are mapping T is a linear
Hmm.
operator by A.
Hmm.
So range of T under this is something inside S that need not be full S. That need not
Yes.
be. I have said
Um,
that subspace
hmm.
invariant if this happens. So
Okay.
if you take elements in S look like this way,
Hmm.
and if you take another subset S that which is elements are look like this way, 2y minus x comma 0 comma minus x.
Hmm.
This is the range, right? X and y
Hmm.
is coming from R.
Yes. Yes.
So S dash actually sitting inside S, and this is what I
Yes.
want.
Not necessarily equal.
Not necessarily
Not
equal. That no,
not
not
maybe
need
copper.
not be. Not need not be equal actually. They need not be
Okay.
equal. In fact, most of
Hmm.
the time they are not equal. Invariant subspace means there has to be just it will be just land there. That's all.
Okay.
The image will be
Okay.
land in the subspace. Okay. So I hope clear it is.
Thank
This
you,
is
sir.
invariant subspace. Okay.
Yes.
So any other doubt, if you anyone of you have, you can ask me. I will try to explain. This is problem number 7. So I will go to problem number 8. So problem number 8. So problem number 8, what it says, let V be a finite dimensional vector space over F and W1, W2, W3 are be any proper subspace of V such that W1 plus W2 plus W3 is V. Okay, no direct sum is given here. Then V is equals to this one is incorrect. Be any proper subspace of V, just only giving the W1, W2, W3 proper subspace of V. First one whether first one is correct or not. So let me recall once that if we have two subspace or k number of subspace W1, W2, Wk, then we can write W1 direct sum all the way Wk. We can write this one. This is what it is. We mean this is what it is called in general that W1, W2, Wk are independent. This if and only if that Wi intersection W1 plus all the way plus Wi minus 1 plus Wi plus 1 plus Wk all the way. This has to be 0. That means each Wi with the sum of the remaining part of this sum has to be intersection has to be 0. Or, I mean, this is what it is. I just want to say that Wi intersection W1 plus Wi minus 1. So let me write it clearly. This is what already I mentioned in today's tutorial as well. So Wi intersection W1 plus all the way plus Wi minus 1 plus Wi plus 1 plus all the way plus Wk. This has to be 0 for all I. Then we can write that W1 direct sum W2 plus Wk equals to 0. And this fact is equivalent that if alpha 1 alpha I is in Wi and summation of alpha I is equals to 0, that should imply that each of alpha I has to be 0. This is what it is same fact. This full fact is equivalent to this full fact. This is equivalent. Okay. Now, so here it is asked that V is a finite dimensional vector space and W and W2 are any proper subspace of V, then such that we know that W1 plus W plus W3 is V. Then whether this holds or not. The answer is no. So let me give you a counter example. For A, W is actually okay. For A, uh, let us take W is equals actually span of 1 0 0 0 1 0. Okay, and W2 actually span of 0 1 0 0 0 1, and W3 actually span of 1 0 0 0 0 1. So clearly you can say that W1 plus W2 plus W3 that will be the space V clearly because that contains every element. Okay, but W1 intersection, I mean V is not equals to, that's clear, V is equals to not equals to W1 direct sum W2 direct sum W3. That is not correct because they are not disjoint. W1 i's are not disjoint, so there has to be disjoint. This is the basic necessity, because if Wi intersection W1 plus W2 plus Wi minus 1 plus Wi plus 1 plus Wk is 0, that implies Wi, this specific property will give that Wi intersection Wj has to be 0 for all I not equals to j. This is the basic necessity, but this basic necessity fails here. So that's why, so Wi's are not mutually disjoint. They has to be mutually disjoint at least. This is what it is, the minimum basic criteria. So that's why the first option is incorrect. The third option, here is a general formula. So let me write this one. So V is a vector space. V is a vector space, that's clearly W1 plus W2 plus W3. This is written. So why we know that if V is equals to something like some subspace like V1 plus V2, then dimension of V is equals to dimension of V1. This is another theorem. Okay, we know that. Let me write the statement. So I'll use that for theorem. So to conclude this one. So this third option is also not correct, because okay, let me say why third option is not correct. From here we can say, in this case the vector space V is equals to R3. Clear? In this case, vector space V is equals to R3. So for option B, dimension of V is equals to 3. In this case, the above example, dimension of each Wi is actually 2, and W1 intersection W2, that will contains only the 0 1 0 0. That is, dimension of this one is actually 1. Dimension of, in fact, W2 intersection W3, that is equals to 1, and dimension of W1 intersection W2, that is again 1. Okay, there is no problem with this. Now the option here, it is asked that dimension of V is equals to this or not. So let me check. Left hand side is 3, that's clear. Right hand side is 2 plus 2 plus 2 minus 1 minus 1. So what it is, 6 minus 1, that is 4. Is it matching? It's not matching. Okay, so it is clearly says that it these facts, this clearly says that dimension of V is not equals to dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1 intersection W2, and what are the other option? W1, W3. In fact, here is the one important. In fact, here is the one. In fact, the correct expression is. In fact, the correct formula is if W1, W2, W3 are subspace of V, and V is equals to W1 plus W2 plus W3, then dimension of V, this is the correct formula, dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1 intersection W2 minus dimension of W2 intersection W3 minus dimension of W1 intersection W3 plus dimension of W1 intersection W2 intersection W3. This is what it is, the correct formula. So this is already the correct formula. So that's why the second option is incorrect. That's clearly from here one can say. And the third option is also incorrect with this counter example. Why the third option is incorrect? So let me check once. So dimension of V in this counter example, dimension of V is 3. V is actually the R3, right? And the dimension of W1 is 2, dimension of W2 is 2, and dimension of W3 is 3. But in this case, W1 intersection W2 intersection W3 is 0. Clearly W1 intersection, because can you find a vector which is both in W1, W2 and W3? In the first example, in the above example, dimension of W1 intersection W2 intersection W3 is actually 0. So that says that dimension of V, which is actually 3, that is not equals to dimension of W1 plus dimension of W2 plus dimension of W3 minus dimension of W1 intersection W2 intersection W3. So in fact, this is as I have said, this is the correct formula for three subspace V1, W1, W2, W3. The dimension of W1 plus W2 plus W3 is equal to dimension of W1. This is the correct formula. This is what it is. Except this formula, any formula has been given, you can create a counter example which will I mean, here it is not giving any description regarding W1, W2, W3 is giving that, only giving that they are proper subspace. This is what it is given. But still you can always create a counter example which if you are given any expression except this one, and you can create a counter example which will counter that particular expression. So that's why third option is incorrect. Now let's come back to the second option. So sorry, third option is incorrect. So automatically the fourth option will be correct, but let me check this one. So what it is says that V is equals to W1 plus W2 direct sum W3 if W3 intersection W1 equals to 0, W3 intersection W2 is equals to 0, and W3 intersection W1 plus W2 is equals to 0. So here one can clearly say is that, so you have okay, here it is explained. Fourth option is that, D option is that V is equals to W1 plus W2, this with direct sum W3 if given that W3 intersection W1 is equals to 0. I think this is what it is, the W1 W3 intersection W1 W3 intersection W2, W3 intersection W2 is equals to 0, and third option is the W3 intersection W1 plus W2 is 0. W3 intersection W1 plus W2 is 0. This is what it is given, right? Yeah. So this is what it is given. So whether in that, with these three conditions, can we write this one? So first of all, consider W1 plus W2. This is itself is a single subspace. Okay, let me write this as W. And you have another that is W3. Sum of two subspace is again subspace. Union need not be, okay. So now, and V can be written W direct sum W3 if V is equals to W plus W3 and W intersection W3 is equals to 0, and this is what it is given here. Okay, this is what is direct sum formula. You have two subspace W and W2. Their sum is direct sum if they are disjoint. Okay, so that is what it is happened. So that's why the fourth
Last
option is
condition is condition is enough.
Yeah, so these two are actually invalid. I mean,
Yes.
not necessary. In fact, if
Not necessary.
last one holds, then the first two also holds. Okay.
Yes.
W3 intersection W1 plus W2 is equals to 0. This will show that W3 intersection W1 is equals to 0 and W3 intersection W2 is equals to 0. Because if it is not, for example, there is something X non-zero, then you can write that X itself in this one, right? Because W2 is a subspace that has 0. So that means there exists an X which is in, for example, X is in W3 intersection W1. That means X is in W3 and X is in W1. But X is in W1 means X is in W1 plus W2. There is no doubt problem with this, because any element in W1 W2 must be element should be an element from W1 and element from W2. And you can by default you can choose the element from W2 as 0. So that says that X should be in W3 intersection W1 plus W2. So that will contradict the fact that this one. So that's why if you have this, then you will automatically give these two. There will not be any 0 element. Okay. So this is why the fourth option is the correct options. So is this clear? Any even very simple doubt also you can ask. I'll try to explain. Okay. I hope it is clear. Even if you have doubt and I'm going to the next problem, you can still pause me and I will try to explain. Okay, so maybe this is the last problem for today's tutorial. So what it is says, let T be a linear operator on a finite dimensional vector space V over the field F. Give him that 4, 5, 6 are the eigenvalues of operator T. Okay, so these are the eigenvalues of the operator T such that I equals to E1 plus E2 plus E3 and T is equals to 4E1 plus 4E2 plus E3, then this is, but here it is missing many facts, I think. Okay, so here may be missing many facts, so let me, E1, E2, E3 are the projections for which this happens. Okay, this is diagonalizability fact, but here I think it needs some more given that these are eigenvalues of T. And here is the one more fact, and Ei Ej is equals to 0. This is also needed for I not equals to j. Then which of the following is the correct options? Which of the following is here will be interesting fact. You have to find E1. So T is diagonalizable here, but That's not separate thing, but I have to find E1 and E2. We have to find both of them, E1 and E2. So clearly here, whenever you have this one, T is diagonalizable. So here is a theorem, very interesting theorem. I can use that theorem, and I think I can obviously use that theorem, but I am trying to say anything can be done without using that theorem. I hope anything. Yeah, I think I can use easily. So T is giving like this way. So T minus 5i. So what it is? T minus 5i is equals to 4e1. I'm just avoiding the. Um, I'm trying to avoid very another type of. I mean standard theorem. I'm just trying to using the calculations, usual calculations. So this will be like 3e1 plus 4e2 plus 5e3. Okay. So T minus 5 is look like this way. Okay, sorry. But T minus 5i I have written. So okay, sorry, 5i. Sorry, yeah. That's why I'm missing mistakes. Minus E1, second one will be 0, and plus E3. I have to find E1, okay. And similarly, if I can T minus 6i, so what I'm just looking from here, you can do that. So what will give E1 plus 5, E2 plus 6, E3 minus 6 of E1 plus E2 plus E3. Here I am using the fact that I equals to E1 plus E2 plus E3. So you don't need Eij. This is not needed actually. Yeah, this is true. This is maybe not needed. You can directly from calculate here. So this will be equals to uh, 6 E3 will be outside, and this will be 2 E1 minus E2. This is what you will have. Okay, and then you need that one. And ei ej is equals to 0 if I not equals to j. So now let me calculate this one. Let t minus 5i and t minus 6i. What it will be? It will be minus e1 plus e3 whole into minus t e1 plus e2. So clearly this will be plus 2 e1 square, and that is again e1 because e1 is projection. Let me still write it. Then e1 e2 that will be 0 minus 2 e3 e1 that will be 0 plus e3 e2 that will be 0, because we have used that fact ei ej is equals to 0 for I not equals to 0. So that is equals to 2 e1. So basically what I got, e1 is equals to 1 by 2 t minus 5i t minus 5i t minus 6i. So this is the correct option, this is incorrect option. So let me find E2. So for E2, you can look at, we need to find T minus 4i. So let me find T minus 4i. T minus 4i is equals to, T is equals to 4e1, 5e2, 6e2, 4e1, 5e2 plus 6e3 minus 4 into e1 plus e2 plus e3, that is equals to E2 plus 2E3. So I want to calculate T minus 4i into T minus 6i. So this will be like E2 plus 2E3 into T minus 6i is minus 2E1 minus E2. So this will be minus 2 E2 E1, which will be 0 because Ei Ej is equals to 0 if I not equals to j, minus E2 square, which is E2 itself, and minus 2 to 4 E3 E1, which is itself 0, minus 2 E3 E1, which is 0, that is equals to minus E2. So basically what we got, E2 is equals to minus T minus 4i T minus 6i. So which option is correct? This one is the correct option, so this is incorrect option. So because it equals to minus T minus 4i minus into T minus 6i. So this is interesting. So this is clear, right? I hope this is clear. Yeah. So but here I just want to mention one theorem, and I will close today's session after that. Here is one not standard thing, not theorem, basically. It's a standard thing. Whenever, if T, this is a theorem you can say, if T is a linear operator from V to V, be a linear operator on a finite dimensional vector space V over the field F, C1, C2, Ck are distinct eigenvalues, of T. Okay, then if these are the distinct eigenvalues of T, are of T, then and T is diagonalizable, then there exists all linear operators E1 all the way Ek on V such that T is equals to C1 E1 all the way plus Ck Ek, and I is equals to E1 plus E2 plus all the way plus Ek, and next is that Ei Ej is equals to delta Ij. That means either it is no, not delta Ij, delta Ij. I can Ei Ej is equals to 0 if I not equals to j, if I not equals to j, and Ei square is equals to y, that is projection. This is 1, this is 2, this is 3, and the third is that range of Ei is equals to the null space of T minus Ci. On the other hand, if we have a distinct value C1, C2, Ck scalar, and then a linear operator T can be written like this way for some operators E1, E2, Ek, and I is equals to, and this operator satisfying the condition like that I equals to E1 plus E2 plus Ek, and Ei Ej equals to 0, and Ei square equals to Ej, then T will be diagonalizable. Okay, and with the distinct eigenvalue C1, C2, Ck, and range of Ei will be the null space. But the main point what I want to say, that is that in that case, if you remember one theorem I have said, T is diagonalizable then if its minimal polynomial is completely factorized into the linear factors, okay, distinct linear factors, right? Minimal polynomial must be of the form x minus c1 all the way x minus ck, right? Now here EIs are basically, the EI is actually the polynomial, right? This is polynomial px, right? Px. So EIs are basically x minus c1 all the way x minus ci minus 1, x minus ci plus 1 all the way x minus ck by ci minus 1, ci minus c1, ci minus ci minus 1, ci minus ci plus 1 all the way ci minus ck. Sorry, this is not EI. Basically, EI are actually polynomial of this. EI are actually polynomial. You can replace. This is the polynomial. Okay. If f I x is look like this way, then EI are actually f j t. This is what it is. You can check. I hope I have written correctly without the sign. I hope I have still written correctly. So if you have a diagonalizable linear operator, then we have this type of theorem. So in this theorem, these EI operators are actually some polynomial of T. And what is the polynomial? That polynomial actually look like this way. This is something called Lagrangian polynomial or something like this. Okay, so this is what I wanted to say. So anything else? Do you have any doubt? regarding this problem or any other regarding the course content? So if you don't have any doubt, then we can stop here. Yeah. So thank you everyone. So I will close in few seconds. So if you have any doubt, you can ask. Otherwise, I'll close today's tutorial.